Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on Theory of Numbers, lecture number 33, in which I will discuss Wilson Theorem and its examples. Before proving Wilson's theorem, I would like to give you some basic ideas which inspires for the Wilson theorem. Let P be a prime number and let P equal to 11. Then P minus 1 equal to 11 minus 1 equal to 10. Factorial 10 equal to 1 multiply 2 multiply 3 multiply dot 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 multiply 10. Let A be a set containing these numbers 1, 2, 3 dot 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 10. If a small a belongs to capital A, then small a is greater than equal to 1 and less than equal to 10. That is, A is greater than equal to 1 and less than equal to 11 minus 1. Let this is number 1. Let us consider a linear congruence. Ax is congruent to 1 modulo P. This is number 2. Here P equal to 11, A is greater than equal to 1, less than equal to 11 minus 1. Therefore, we may write Ax congruent to 1 modulo 11. This is number 3. Since A is greater than equal to 1 and less than equal to 11 minus 1, therefore GCD of A and 11 equal to 1. Therefore, we get a unique solution of 3. Let A bar be the solution of 3. Therefore, A bar is congruent to 1 modulo 11. A bar is called inverse of A modulo 11. Now, let A equal to 2 implies that GCD of 2 and 11 equal to 1 and 2x congruent to 1 modulo 11. Let this is number 4. Since 0 is congruent to 11 modulo 11, because 0 minus 11 is minus 11, which is divisible by 11. Let this is number 5. Adding 4 and 5, we get 2x plus 0 is congruent to 1 plus 11 modulo 11, implies that 2x is congruent to 12 modulo 11, implies that x is congruent to 6 modulo 11, since GCD of 2 and 11 equal to 1. This is number 6, which shows the inverse of 2 modulo 11. Therefore, 6 is inverse of 2 modulo 11. Therefore, we may write, if A equal to 2, then A bar equal to 6, and A bar is congruent to 1 modulo 11. That means 2 multiply 6 congruent to 1 modulo 11. Let this is number 7. Again, let A equal to 3 and GCD of 3 and 11 equal to 1. Now, 3x congruent 1 modulo 11. This is number 8. Adding 5 and 8, we get 0 plus 3x is congruent to 11 plus 1 modulo 11, implies that 3x is congruent to 12 modulo 11, implies that x is congruent to 4 modulo 11, since GCD of 3 and 11 equal to 1. Therefore, 4 is inverse of 3 modulo 11. So, we may write three multiply 4 congruent 1 modulo 11. Let this is number 9. Now, 5x congruent to 1 modulo 11. Since GCD of 5 and 11 equal to 1, Let this is number 10. Since 0 is congruent to 44 modulo 11, because 0 minus 44 is minus 44, which is divisible by 11. Let this is number 11. Adding 10 and 11, we get 5x plus 0 is congruent to 1 plus 44 modulo 11, implies that 5x is congruent to 45 modulo 11, implies that x is congruent to 9 modulo 11, since GCD of 5 and 11 equal to 1. Therefore, 9 is inverse of 5 modulo 11. Therefore, 5 multiply 9 is congruent to 1 modulo 11. Let this is number 12. Now, let 7x is congruent to 1 modulo 11. Since GCD of 7 and 11 equal to 1, let this is number 13. Now, 0 is congruent to 55 modulo 11. Since 0 minus 55 is minus 55 and minus 55 is divisible by 11. Let this is number 14. Adding 13 and 14, we get 7x plus 0 is congruent to 1 plus 55 modulo 11, implies that 7x is congruent to 56 modulo 11, implies that x is congruent to 8 modulo 11. Therefore, 8 is inverse of 7 modulo 11. Therefore, we may write 7 multiply 8 is congruent to 1 modulo 11. Let this is number 15. Now, 10x is congruent to 1 modulo 11. Let this is number 16. Since 0 is congruent to 99 modulo 11, let this is number 17. Adding 16 and 17, we get 10x plus 0 is congruent to 1 plus 99 modulo 11 implies that 10x is congruent to 100 modulo 11 implies that x is congruent to 10 modulo 11. Therefore, 10 is inverse of 10 modulo 11. We may write 10 multiplied by 10 is congruent to 1 modulo 11. This is number 18. 1 multiply x is congruent to 1 modulo 11 implies that x is congruent to 1 modulo 11. This is 19. Therefore, 1 is inverse of 1 modulo 11. Therefore, 1 multiply 1 is congruent to 1 modulo 11. Let this is 20. We may also write 10 is congruent to 10 modulo 11 because 10 minus 10 equal to 0 which is divisible by 11. Let this is 21 and 1 is congruent to 1 modulo 11 because 1 minus 1 equal to 0 which is divisible by 11. Let this is 22. By using product rule of congruences by multiplying 7, 9, 12, 15, 21 and 22, we get 2 multiply 6 multiply 3 multiply 4 multiply 5 multiply 9 multiply 7 multiply 8 multiply 10 multiply 1 is congruent to 10 modulo 11 implies that this is 1 multiply 2 multiply 3 multiply 4 multiply 5 multiply 6 multiply 7 multiply 8 multiply 9 multiply 10. That means factorial 10 is congruent to 10 modulo 11. We may also write this as factorial 10 is congruent to minus 1 modulo 11. Let this is number 23, this is number 24. So, for a prime number P, we may get factorial p minus 1 is congruent to minus 1 modulo 11, which is the Wilson theorem. Therefore, from above ideas, we may conclude that for a given prime number p, number 1, the integers 1 and p minus 1 are their own inverse modulo p. Number 2, the remaining integers p minus 3. Here we have number of integers p minus 1. If we subtract it by 2, means numbers 1 and p minus 1 removed from this list, then remaining number of integers be p minus 3. These remaining p minus 3 integers form p minus 3 by 2 pair of the form a and a bar. A bar be the inverse of a modulo p. And finally, factorial p minus 1 is congruent to p minus 1 modulo p. Now we discuss about Wilson theorem. Firstly, we state the theorem. Let p be a prime number, then factorial p minus 1 is congruent to minus 1 modulo p. Now we prove this. Let p be a prime number. Now let p equal to 2. Then p minus 1 equal to 2 minus 1 equal to 1. Since 1 is congruent to minus 1 modulo 2, since 1 minus minus 1 is 2, which is divisible by 2, implies that factorial 1 is congruent to minus 1 modulo 2. We may write this: factorial 2 minus 1 is congruent to minus 1 modulo 2. Implies that in place of 2 we write p. Factorial p minus 1 is congruent to minus 1 modulo p. Therefore, it is true for p equal to 2. Now, let p greater than 2. Then factorial p minus 1 equal to 1 multiply 2 multiply 3 multiply dot 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 multiply p minus 1. Let a is greater than equal to 1 less than equal to p minus 1. Therefore, GCD of a and p will be equal to 1. Hence, the linear congruence AX is congruent to 1 modulo p has a unique solution. Let this is number 1 and this is number 2. Let A bar be the solution of 2. Therefore, A bar is inverse of A modulo P. Therefore, A bar is congruent to 1 modulo P. This is number 3. Since A bar is greater than equal to 1 and less than equal to P minus 1, therefore GCD of A bar and P equal to 1. Since inverse of 1 modulo P equal to 1 and inverse of P minus 1 modulo P equal to P minus 1. Remaining integers 2, 3, P minus 2 may be grouped in P minus 3 by 2 number of pairs such that in each pair one integer is inverse of other modulo P. Let A bar be a pair among these in which A bar is the inverse of A modulo P. Therefore, A bar is congruent to 1 modulo P. Here A is greater than equal to 2, less than equal to P minus 2. Let this is number 4. Again, 1 is congruent to 1 modulo P. This is number 5. And P minus 1 is congruent to P minus 1 modulo P. This is number 6. Now, from 4, 5 and 6, by rule of product of congruences, we get 1 multiply 2 multiply 3 multiply P minus 1 is congruent to P minus 1 modulo P. Implies that factorial P minus 1 is congruent to P minus 1 modulo P. Implies that factorial P minus 1 is congruent to minus 1 modulo P. Proved. Conversely, let n be a positive integer and factorial n minus 1 congruent to minus 1 modulo n. Let this is number 7. If possible, let n be a composite integer such that n equal to a multiply b. This is number 8. Therefore, a divides n. This is number 9. From 8, a is greater than 1, less than n. b is greater than 1, less than n. Implies that a divides factorial n minus 1. This is number 10. From 7, here n divides factorial n minus 1 plus 1. This is number 11. From 9 and 11, we get here in 9 a divides n. Here n divides factorial n minus 1 plus 1. A divides factorial n minus 1 plus 1. Let this is 12. From 10 and 12, we get a divides factorial n minus 1 plus 1 minus factorial n minus 1. Implies that a divides 1. This is number 13. But here we see that a is greater than 1. So 13 is not possible. That is, our assumption n is a composite number is wrong. Therefore, n is a prime number. Hence, converse is proved. Now, we give an example in which by applying Wilson's theorem so that factorial 10 minus 32 is congruent to 0 modulo 11. Let p equal to 11. Therefore, by Wilson theorem, factorial p minus 1 is congruent to minus 1 modulo p. Implies that 11 minus 1 factorial congruent minus 1 modulo 11 implies that factorial 10 is congruent to minus 1 modulo 11. This is number 1. Now 32 is congruent to minus 1 modulo 11 because 32 minus 1 means 33 is divisible by 11. This is number 2. Subtracting 2 from 1, we get factorial 10 minus 32 is congruent to minus 1 minus minus 1. This is 0 modulo 11. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.